Hello class, welcome to Stat 1200. I am your instructor William Buellman, and today we are covering section 6.2, Sampling Distributions and the Central Limit Theorem. Our objectives for today are to be able to construct the sampling distribution of a sample mean, and to use the central limit theorem to compute probabilities involving sample means. In real situations, statistical studies involve sampling several individuals then computing numerical summaries of those samples. Most often, the sample mean X bar is computed. If several samples are drawn from a population, as above in the diagram, they are likely to have different values for X bar. Because of the value of X bar varies each time the sample is drawn, X bar is a random variable. For each value of the random variable X bar, we can compute a probability. The probability distribution of X bar is called the sampling distribution of X bar. Tetrahedral dice are shaped like a pyramid with 4 faces. So this is a 4-sided dice. Each face corresponds to a number between 1 and 4. Tossing a tetrahedral die is like sampling a value from a population of 1, 2, 3, 4. We can easily find the population mean, mu, which is 2.5, and the population standard deviation, sigma, which is 1.118. Suppose that a tetrahedral die is tossed 3 times. The sequence of the 3 numbers observed may be thought of as a sample size of 3. We may get such samples as 111, 112, 113, and so on. The table displays all possible samples of size 3 and the sample mean X bar of each. The mean of all the values of X bar, so this is the mean of all the means, mu sub X bar, is equal to 2.5, and the standard deviation of all the values of X bar is sigma sub X bar, which equals 0.6455. So below you see this table. This shows all the possible combinations. If you were to roll 4-sided dice 3 times, these are all the possible combinations you could get with their X bars. Next, we compare these values to their population mean and their population standard deviation. The mean of the sampling distribution is mu sub X bar, which equals 2.5, which is the same as the mean of the population mu, which is equal to 2.5. This relation always holds. The mean of the sampling distribution is denoted as mu sub X bar and equals the mean of the population, so mu sub X bar is equal to mu. The standard deviation of the sampling distribution is sigma sub X bar, which equals 0.6455, which is less than the population standard deviation of sigma, which was equal to 1.118. It is not obvious how these two quantities are related, though. Note that if we take sigma sub X bar, which is equal to 0.6455, that is equal to 1.118 divided by the square root of 3, which, if we remember right, that 1.118 was sigma, so that's equal to sigma over the square root of 3. But also recall that the sample size n was equal to 3, which suggests that our sigma sub X bar is actually equal to sigma over the square root of n. The standard deviation of the sampling distribution, sometimes called the standard error, is denoted by sigma sub X bar and is equal to the standard deviation of the population divided by the square root of the sample size. So sigma sub X bar is equal to that population standard deviation over the square root of the sample size. So that's what we're getting at here. Example 1. Among students at a certain college, the mean number of hours of television watch per week is mu, which equals 11.2. and the standard deviation is sigma, which equals 4. A simple random sample of 25 students is chosen for a study of viewing habits. Let x bar be the mean number of hours of TV watched by the sampled students. Find the mean mu sub x bar and the standard deviation sigma sub x bar of x bar. So the mean of x bar is mu sub x, which remember is just equal to mu, which we already know is 11.2. Okay, reminding you the sample size was 25, therefore the standard deviation of x bar, which sigma of x bar was equal to sigma over the square root of n. And we know sigma was 4. And we know the sample size is 25. So we have 4 divided by the square root of 25, which is equal to 0.8. So our mu sub x is equal to 11.2, and our sigma sub x bar is equal to 0.8. Consider again our tetrahedral die example from before, the four-sided dice. The sampling distribution for x bar can be determined from the table of all of the possibilities of x bar. So again, here was all the possible values of x bar based off of the sample. The probability that the sample mean is 1 out of 64, because there's only 1 out of those 64 outcomes where the sample mean was 1, or equivalently that decimal. Because out of the 64 possibilities, as I said before, only 1 had a sample mean equal to 1. Similarly, the probability that x bar is equal to 1.33 is 3 out of 64, or that decimal, because there are 3 samples whose mean was 1.33. The remaining probabilities are as follows. So in this table below shows the remaining probabilities. In the tetrahedral die example, the population was 1, 2, 3, 4. When a die is rolled, each number has the same chance of appearing 1 out of 4. The probability histogram for the sampling distribution of x bar with a sample size of 3 is obtained from the sampling distribution on the previous slide. The probability histogram for the sampling distribution looks a lot like the normal curve, whereas the probability histogram for the population does not. Here are the 2 probability histograms. Here's the one for the population on top. It's just 1/4, 1/4, 1/4, 1/4. And below is the probability histogram for the sample, which you notice looks very much like a curve. It starts off low on the left-hand side, kind of comes up to a high point in the middle, and then drops back down, which reminds us a lot of a curve. Remarkably, it is true that for any population, if the sample size is large enough, the sample mean x bar will be approximately normally distributed. For a symmetric population like the tetrahedral die population, the sample mean is approximately normally distributed even for a small sample size of 3. If a population is skewed, a larger sample size is necessary for the sampling distribution of x bar to be approximately normal. Consider the following probability distribution. So we can see that it is skewed because it has a high probability on the left-hand side, and then on the right-hand side it is very low. This is not a normal distribution of probability, so we see the skew here, so we know we must need a larger sample size. Below are the probability histograms for the sampling distributions of x bar for samples of size 3, 10, and 30. Note that the shapes of the distributions begin to approximate a normal curve as the sample size increases. So you notice over here with the sample size of 3, not very normal curved. As the sample size gets to 10, okay, it's starting to pull towards the middle. It's starting to look more normal curved, but there's still some skew. And as we get to 30, we can see we have a much more normal curve. It's centered around the middle, and this is what we expect. So this is looking a lot better. The sample size of the sample needed to obtain approximate normality depends mostly on the skewness of the population. In practice, a sample size n greater than 30 is large enough. So what that's saying is if you have a sample size greater than 30, it should be large enough for the sample to be approximately normal. The remarkable fact that the sampling distribution of x bar is approximately normal for a large enough sample from any distribution is part of one of the most used theorems in statistics called the central limit theorem. And here's what the central limit theorem states. Let x bar be the mean of a large n greater than 30 simple random sample from a population with mean mu and standard deviation sigma. Then x bar has an approximately normal distribution with mean mu sub x bar is going to be equal to mu, and the standard deviation sigma sub x bar is going to be equal to sigma divided by the square root of n. That is the central limit theorem. The central limit theorem applies for all populations. However, for symmetric populations, a smaller sample size may suffice. If a population itself is normal, the sample mean x bar will be normal for any sample size. So what that is saying is if you know the population is normal, no matter what your sample size is, it will be normal as well. But that is only if you know the population itself is normal. Example 2. A sample size of size 50 will be drawn from a population with mean mu equaling 17 and standard deviation sigma equaling 5.3. Is it appropriate to use the normal distribution to find the probabilities for x bar? The answer is yes. By CLT, which is the central limit theorem, since n is greater than 30, x bar has an approximately normal distribution. Example 3. A sample size of 7 will be drawn from a normal population with mean mu equaling 27 and standard deviation sigma equaling 6.2. Is it appropriate to use the normal distribution to find probabilities for x bar? For here, there's two things we have to remember. With the central limit theorem, you have greater than 30 and comes from approximately normal. So in this case, our sample size was not greater than 30. But since the population it came from was approximately normal, we know that x bar will be approximately normal, and that is appropriate, so yes, we can use the central limit theorem. Example 4. A sample size of 24 will be drawn from a population with mean mu equaling 35 and standard deviation sigma equaling 1.2. Is it appropriate to use the normal distribution to find the probabilities of x bar? No, since the population is not known to be from a normal distribution and n is not greater than 30, so neither one of those conditions has been satisfied, we cannot be certain that x bar has an approximately normal distribution. Based on data from the U.S. Census, the mean age of college students in a recent year was mu, which is equal to 22 years, with a standard deviation sigma of 6.2 years. A simple random sample of 64 students is drawn. What is the probability that the sample mean age of the students is greater than 23 years? The sample size is 64, which is greater than 30. Therefore, we may use the normal curve and the central limit theorem. We compute mu sub x bar and sigma sub x bar as, reminder, mu sub x bar is equal to mu, which is equal to 22, and sigma sub x bar is equal to sigma over the square root of n, which is equal to 13.5 over the square root of 64, which is equal to 0.775. So now we want to find the area under the normal curve, which is z, which equals xi, the thing we're interested in, minus mu, the population standard deviation, over sigma sub x bar, which equals 1.29. So we're going to use table A2 to find the area to the left of z. So here's table A2, and remember we have to go to the row with 1.2 and the column with 0.09, and we find that value where they intersect right here, highlighted in yellow. So using table A2, we find the area to the left of z, 0.9015. The probability that the sample mean age of a student is greater than 23 years is, remind you, the complement rule. We want greater than, not less than, and this is less than 23 years, so we have 1 minus 0.9015, which is equal to 0.0985, which is 9.85%. So we have a 9.85% chance that the mean age is greater than 23. Example 6. Hereford cattle are one of the most popular breeds of cattle. Based on the data from the Hereford Cattle Society, the mean weight of a 1-year-old Hereford bull is 1,153 pounds, with a standard deviation of 82 pounds. Would it be unusual for the mean weight of 100 head of cattle to be less than 1,125 pounds? So 100 head of cattle means a group of 100 cattle. Since the sample size is 100, which is greater than 30, we can proceed with the central limit theorem using the normal curve. Thus, we get mu sub x bar is equal to 1,153, and sigma sub x bar is equal to 82 over the square root of 100, which is equal to 8.2. We have to find the area under the normal curve, which is xi minus mu over sigma sub x bar, which equals negative 3.41. And again, we're going to use table A2 to find the area to the left of this negative 3.41. Using table A2, we can find the area to the left of negative 3.41, which we have highlighted here as 0.0003. Thus, this probability, right, of 0.0003 is less than 0.05, which is our cutoff for unusual. So it would be unusual for that to happen. And since the probability is 0.0003, which is less than 0.05, our cutoff, it is unusual for the sample mean to be less than 1,125 pounds.